Also lost my time through Cramers class. Mr. Smith, who would you say like? So like you, Miss Mixler, are like the calc. You and like Mixler and Schultz are like the calc department. Who would you say like your department, like the calc department, and what other like teacher department like talks the most?
Probably pre-cal because it's right before calculus, and like Mr. Schultz also does pre-cal. So that's like a connection to pre-cal.
Wait, is it Mr. Schultz or Coach Schultz?
I guess if he's your coach, you probably call him Coach Schultz. But he
'Cause,
didn't,
like,
he didn't coach me in anything. So.
I know, like aren't the football coaches like just called coach in these classes?
I don't know. I don't sit in any of their classes either.
I've only ever known Mr. Schultz.
Well, I call him Tim. So.
I called him Tim once. He got mad at me. I said, I called him Timothy, and he was not too pleased with that.
You just start calling.
We get no bonuses this test, right?
We kind of have
I curved it a little bit.
I was checking my subspaces.
104, no 105.
You think the grades are like always better in linear algebra than multi?
For some people. I still had people getting 20s on the last test.
Oh, 'cause there's, I guess it's better for my
Yeah.
brother and.
I don't get it.
Is the difference like as drastic linear algebra, where it's either they get really high or really low and nothing between, or is it like a nice even spread?
There's not an even spread. There's not much in between probably B's and fails on our linear tests because I feel like you're usually like getting most of it and getting A's and B's, or it's like
So it's in the window between like 60 and 90 is kind of void.
I don't think it's like
maybe like 80.
most like the 80, isn't that most like just
Is what?
Most like mistakes, or is it like
Yeah, a ton of the mistakes are small, so it's a lot of -2s for people.
I did that a lot because I went back to check my subspaces and they were orthogonal. I didn't have
Yeah.
time to change it. So I just, like,
So for a lot of people, it's like a ton of arithmetic mistakes add up to maybe 10 points or whatever. But most people, it's not like you're doing nothing that makes any sense. That's not happening for most people. Okay. Today we are doing lesson 19. This would have normally been on the last test. This really goes well with 17 and 18. It's a good grouping. So don't love that it's not on that one, but it'll now be on the next test. The problem set is going to have this 19 and 20 on it, and it's due Friday, so you don't really have to like think about this or do stuff over spring break. When we come back, Friday's lesson will be grouped with some of the early lessons for when we get back on the next problem set. But Thursday we have no class and all that stuff. So today's lesson's pretty short because it's mainly kind of some applications of some formulas. So my normal way of sharing is not working. I don't know if something needs to be updated, but I'm going back to the old way, which isn't as great because it doesn't look very good up here. Okay, where's my waiting room here? Participants. There it is. All right, so today we're looking at what's called Cramers rule, which is another way of solving AX equals B. If you do it correctly, it's going to give you the same answer as if you had solved it a different way. And it also leads us to a method for finding inverses. Inverses are pretty much never super easy unless it's a 2x2. 3x3 inverses using this method won't be bad, but the larger it gets, they use determinants. So you have to remember, like if we have a 5x5 matrix, your determinants will be 4x4, which then have some 3x3s in those, which then have 2x2s in those. So it scales very well if you have like computing power, devoted to solving these things. It's an easy algorithm. It's just a lot of steps, a lot of arithmetic and stuff, the larger it gets. So all today's stuff has to do with determinants. So first, Cramer's rule. Cramer's rule is a way for solving AX equals B. So x1, x2, x3, x4, those are the unknowns in X. A is the A we're used to seeing now since lesson number 1. And then here where you see all the B's, B1 is just A with the first column replaced with vector B. B2 is A with the second column replaced with vector B. B3 would be the same, but with a third column replaced, and so on. And so I'd take these two determinants, divide, and that'll give you the same solution as if you did elimination and find the pivots, find the free variables, all that stuff. Here, there should be no free variables because determinant not being 0 means you have independent rows, independent columns. Every column has a pivot, no free variables, exactly one solution to every B, all that stuff. That's all gonna, Cramer's rule only applies to those situations because the determinant can't be 0. All the ones where we ended up with free variables and infinite solutions, that's when the determinant is not 0, in which case Cramer's rule would not apply. You would have to do one of the other methods that we've done so far. And if you did this with a 2x2, you could kind of show it pretty easily how it would work. Otherwise, I don't know off the top of my head what the proof is for this, but I'm sure there's lots of them out there. I just don't know what it is. Yeah, it's pretty straightforward formula. Really easy for a 3x3 system of equations, or larger systems that have lots of zeros in them. This wouldn't be very bad, but notice all the determinants we're taking. The larger the system, the more those determinants are lots of small calculations that you're having to do. So without a computer or a calculator, this could get hard with a large system. With a computer or calculator, this is a very easy way of solving a system of equations. If you have a computer or calculator, very easy way. All right, so we're going to use Cramer's rule to solve this system of equations. So our setup is the same as we've been doing since the beginning. So I have my matrix A. X would just be my unknowns, x1, x2, x3. And I'm finding where that equals 1, 0, 0. So first thing I would do is I would find the determinant of A. Because if the determinant of A is 0, you don't need to do the rest of the work. You can't be solved with Cramer's rule. It's implying there's a dependent set of rows, columns. There's either infinitely many solutions or no solutions. So we need to find the determinant of A first. You could use any of the methods that we've done up until this point. So here I'm going to use cofactors. And I'm going to use column 3. Since I've got 1s and 0s in column 3, that'll make those calculations not too difficult. So I'll have 1 times the determinant -2, 1, -4, 0. Technically minus 0. Remember that the coefficients of the cofactors change signs as you go across. The 0 obviously won't matter. And then plus a 1 times the determinant 1, 1, -2, 1. So I have 0 minus a -4, which is 4. And then I have 1 minus a -2 is +3. So I have a determinant of 7, which means, again, independent rows, independent columns, exactly one solution for any given B. R equals M equals N. There is an inverse, whatever. All those things come from that same information. And then for each of my little B matrices, for B1, I'm going to take A And I'm going to replace column 1 with vector B, 1, 0, 0. Okay, this being B here. The B and AX equals B. And then I'm going to leave the other 2 columns alone.
That makes it really easy.
Yeah, this is easy because I picked a lot of zeros. And again, the more zeros there are, the more this makes this a very easy way of doing this. Oops, I did that wrong. Sorry, this should be a 0 here. The more zeros, the better. Okay, for B1, we could use cofactors, we could use elimination, or we could just notice this is already upper triangular. Right, so we have a shortcut. The upper triangular, all I have to do is multiply the diagonal to get that determinant. So this is 1 times 1 times 1, which is 1. Which means my first unknown, x1, is 1 over 7. Okay, it's that determinant over the determinant of A. So if I solve this a different way, what I'd find is x1 is 1/7. Okay, it would come out the same no matter what method I'm solving, because there is exactly one solution for any given B because of the determinant. Okay, for B2, this time I'm going to exchange column 2. So I'm going to have 1, -2, -4. Column 2 will be the 1, 0, 0. And then column 3 will be 1, 0, 1. So I take matrix A and I just exchange the second column for this one. Again, you could use multiple methods here. There's a pretty easy cofactor determinant I could use here. So that'll be -1 since I'm starting in the second spot. Remember, this would have a positive cofactor. This one would have a negative cofactor. So it'll be negative determinant of -2, 0, -4, 1. And then I'd have plus 0, -0, which again, we don't really need. So then I have the negative of -2 minus 0, so +2. Which means my second unknown x2 is 2/7. And then for 3, I do the same thing. I'll have the same columns as A in column 1 and column 2. And this time I'll replace column 3 with the 1, 0, 0. And again, I could use cofactors. This is a pretty easy one with cofactors. I could even do things like switch rows. So here, notice if I switch these rows, it'll switch the sign, but it'll give me a lower triangular matrix. Okay, not really any harder or easier than what we already have since we've got so many zeros in here. You could do cofactors pretty easily. But now I could just multiply that main diagonal. And that's negative of -4, +4. So my third unknown would be 4/7. And so that would be my solutions. If we had solved it the way we did on the first test, you'd have gotten the same thing. Your null space would have been 0. So you wouldn't, no free variables, you wouldn't have had extra solutions. It would have been just this one. This would have been the one particular solution that you could find if I did elimination and solved it that way. So again, this is really convenient with a computing device, calculator, computer. This is pretty convenient if you've got a lot of zeros in your matrix or zeros in your equations that you're looking for. This is pretty fast and pretty easy in those situations. Okay, this also can lead us to a formula for the inverse. So right now, if we want to find the inverse of anything other than a 2x2, it's Gauss-Jordan elimination. Here we can kind of develop a formula for finding the inverse. Does not mean it's easier to do, but another way of finding an inverse. All we do is we look here when we did AX equals 1, 0, 0. Notice that was the first column of the identity was our B vector. So we really found the first column of our inverse. Right, the X we just found, if we put it here, I know that if I multiply by that, I'll get 1, 0, 0, which is the first column of the identity. If I found like AY equals 0, 1, 0, and I found AZ equals 0, 0, 1. The other columns of the identity, those will have been the other columns of the inverse. If I put them here, I know that as I multiply A times those, I will get 1, 0, 0 from X and 0, 1, 0 from Y and 0, 0, 1 from Z. So I'll end up with the identity on the other side. So this would be the inverse of A. If I used Cramers rule and solved for 1, 0, 0, 0, 1, 0, 0, 0, 1, it's not bad because there's a lot of zeros and ones and stuff. So it makes that not terrible to do, right? Remember that whenever we substitute this in for a column, all of those B's will be pretty easy to find since there's so many zeros. So this isn't very bad. It's not a bad method to use. Okay, we can use this to find the inverse by just solving for those 3 different things. Remembering that as it gets larger, we'll have 4, 5, 6, 7 of those to do. So again, it adds on time. It adds on space that it takes up. Okay, we have an explicit formula for the inverse. The first formula there is for each individual entry of the inverse. Okay, to find the ij entry of A inverse. So if I have like A inverse, and I'm trying to figure out what would be here, like A21. So then I could use this formula. I is 2, J is 1. So I would find the cofactor of the 1, 2 location. Okay, so I would go to A, and I would find the cofactor of here, okay, 1, 2, which remember is the determinant of what's in these other spaces here. That'll give me the cofactor. I take the determinant of those stuff there. Okay, that'll be my cofactor that I'm talking about. So if I want to know what goes in the 2, 1 spot of the inverse, I take the cofactor of the 1, 2 spot from A, and then I divide by the determinant of A, and that'll be what goes there. I don't tend to use that one because I'm rarely interested in each individual element as much as I want the entire inverse, which is what that second formula is there. It's using the same thing. It's just saying rather than do each one individually, notice that the row and column switches where we're looking, which is why we're using C transposed. C is just called the cofactor matrix. And I believe your homework may have already mentioned the cofactor matrix. But the cofactor matrix is just saying replace each element with its cofactor. So like when I go to find cofactor matrix, I'm replacing like element 1 would be my cofactors of A11, which would be A22, A23, A32, A33. It'd be a little determinant, right? And each of these elements would be little determinants that I'm replacing the element with. Remembering that as I move across, these change signs. This one would be negative, 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 negative. Okay, I transpose that, and that'll basically give me what's in that first box. Don't forget to divide by the determinant, just like we do for our shortcut with 2x2s. Okay, so we'll do an example. If you do a couple of these, they're not, it sounds like a lot. For like a 3x3, it's really not that bad. Again, for a 4x4, each of those elements would be a 3x3 determinant, and each of those 3x3 determinants would be multiple 2x2 determinants. So the larger it gets, still is not like super fast and easy. There is no fast, easy inverse for matrices. The more zeros you have, the more this is pretty easy to do. But Gauss-Jordan elimination is still an option, but again, we've seen that's not super easy to do either. So say we want to find the inverse of A here. Just like before, I would start with the determinant, Because if the determinant is 0, you don't have to keep going. There is no inverse. So rather than do all the other work first, find the determinant of A, make sure there is an inverse. So like here, I'll go with row 2 and I'll use cofactors. But again, we have multiple ways to do it. You don't have to use cofactors. So that'll be -1 times the determinant of 1, 3, 1, 0 plus 0 minus 1 times the determinant of 0, 1, 2, 1. So I have a -1 times 0 minus 3, which is a +3. And then a -1 times 0 minus 2, which will be a +2. So my determinant is 5, which again is fine. There is an inverse. My rows are independent. My columns are independent. This was part of an AX equals B situation. There is a solution for every B. There is exactly one solution for every B. There will be no free variables. The null space is 0. The left null space is 0. I don't know. All that stuff is going to be coming from this. All right. So my cofactor matrix, I would go element by element and think, what is the cofactor of 0? Well, it's the determinant of everything not in that row and column. So it's the determinant of 0, 1, 1, 0. So 0 minus 1, the cofactor is -1. You don't multiply it by A or by whatever, 0 in this case. The cofactor is the other part. When I do the something times the determinant, it's the determinant, not the thing you're multiplying it by. And then you just do that for every spot. Okay, so if I go across, this time, remember as I go across, the sign switches. And then I'll have 0 minus 2. And then as I go across, the sign switches again, so it'll be positive this time. And then this will be 1 minus 0. And then as I go here, this one, the sign will switch again. And then I have 0 minus 3. And then here I'll have 0 minus 6. And then my sign will switch again. And I have 0 minus 2. And then I have 1 minus 0. Sign will switch. And I have 0 minus 3. And then I have 0 minus 1. Okay, so that would be my cofactor matrix unsimplified. Obviously, the little negatives of negatives would cancel out. So this would be positive, 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 positive. So that's my cofactor matrix. So the inverse, I do 1 over the determinant, just like I would with my shortcut. Okay, if we do this on a 2 by 2, we get the same thing as our shortcut. And then I transpose this C. So instead of row 1, 2, 1, I should have a column 1, 2, 1. Instead of row 3, -6, 2, I'll have a column 3, -6, 2. And then row 1, 3, -1 is column 1, 3, -1. Oops. Okay, and that would be the inverse of A. If I did Gauss-Jordan elimination, I would get the same thing, only. Oh yeah, it should be a -1. So this would be, if I did Gauss-Jordan elimination, I'd get the same thing, only the 1/5 would probably be distributed through when you did Gauss-Jordan elimination. But you'd get the exact same matrix. So this is another way of finding it. Pretty easy with a 3 by 3. Okay, a 2 by 2, you get the exact same thing as our normal shortcut. 4 by 4, this wouldn't be bad the more zeros there are. This wouldn't be terrible. But again, as I get larger, there isn't really a fast, simple way of finding an inverse. I would say this, again, would be a lot easier if you're programming than trying to program Gauss-Jordan elimination into something, although you could. This would probably be an easier way to program finding an inverse if you're doing some sort of programming. Okay, determinants can also be used to find area. We technically kind of already did this in multivariable. I don't even remember where it was in multivariable calculus, but it was when we were doing cross products, which are determinants. We did a cross product could give you area of a parallelogram. It's the exact same idea as what we're doing here. We could use geometric ideas, like if we had a triangle graphed on some graph, right? Normally we'd want a base and a height and do 1/2 base times height. And so we could come up with like the distance between these 2 points and get the base. We could come up with the slope of this line and the slope of the line that goes through the other vertex that's perpendicular slope, come up with the equation of a line, find the intersection, find the distance here, get the height, all that stuff. We did that in geometry, okay? And you can do that stuff to find base and height. We could use trigonometry, right? We could use the angles here or inverse trig to get those angles or whatever. Law of sines, law of cosines, all these different ways that we could try and solve to get the base and the height here. If we don't have lengths, if we have vertices. Okay, here with determinants, we can use the vertices and find the area of a triangle. Okay, so if we have the 3 vertices of a triangle, we could plug them in here. You could scale this up to get areas of other shapes, but all polygons can be broken into triangles. So I would just use this one and do however many triangles are in your hexagon or however many triangles are in your trapezoid or whatever. If it's not a polygon, obviously it cannot necessarily be broken up into triangles, in which case you probably wouldn't use determinants. I tend to use the second one because I would rather do a 2x2 determinant. The second one is basically saying if we just translate the entire shape over to one vertex is on the origin, you knock out a row and a column of your determinant. So we could do it in a 2x2 instead of a 3x3. The 3x3 is nice because it's just explicit. Just plug in your vertices, take a determinant. I tend to just want the 2x2 and I don't find the translation very difficult. So I like the second one there is basically just moving one vertex to the origin.
Wait, that A is just
A is area.
okay.
Yeah, that's area. Not a matrix, yeah. All right, so for example, if we had this triangle and you want area, again, using geometry, we could pretty easily find a length of a side to use as the base. The height, you'd have to start using some kind of algebra to figure out what line is perpendicular, what's the length of that little piece that's perpendicular. Again, we have lots of ways we could do that. You guys have probably been doing that since, I don't know, middle school somewhere. But here, we could use a determinant and kind of just this explicit formula with vertices. Again, I tend to like the shift. So if I just shifted the entire triangle, it's not going to change the area. So I'm just going to shift to where one vertex is at the origin. So meaning I'm going to move the whole thing left 3, down 1. So if I move 5, 2, left 3, and down 1, that'll put me at 2, 1. And then if I take 4, 7, and I go left 3, down 1, that'll put me at 1, 6. So this is 1/2 12 minus 1, which is 11 halves. Okay, is the area of this triangle. Again, you could use the 3x3 and use what we've been doing. It's not like it's terrible to find the determinant of a 3x3 matrix, but I don't find the shifting very difficult. Be careful if you switch vertices, you put a different one first, you'll switch the sign of the determinant. So really, I would say you probably want to take the absolute value of what you get. So that if you end up switching them and you get 1 minus 12, you're not telling me the area is negative 11 halves. It really should be a positive number. So since we're finding area, take the absolute value of what you get, because if you took the vertices in a different order, you'll switch the sign. But there's not some specific order you have to put them in. Okay, parallelogram, or again, any polynomial, just think about what it would look like to divide it into triangles. Parallelograms are nice because it's two identical triangles, two congruent triangles. So all I have to do is multiply by 2. If it's not two congruent triangles, you just do 2 of them and add them together, okay, with the different vertices. So like here, again, I would translate the whole thing to the origin. So go left 3, down 2. So the area will be 2 times 1/2, because there's 2 congruent triangles. If I go left 3, down 2, 5, 3 will go to 2, 1. And then 4, 7 will go to 1, 5. And so I'll get 10 minus 1 is 9. And if we have the graph, you can estimate, and you could see 9 is not a bad estimate. If I got 30, I would think something was wrong. Or if I got 1/2, I would think something was wrong. Just looking at the triangle or the parallelogram, I would know that it shouldn't be, I can start counting boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9. Like you kind of start estimating boxes like you again do in elementary school, counting little boxes, and know that 9 is a reasonably good estimate. Okay, if you had some other shape, if it's not super, symmetric and regular, so say we had a pentagon, I would do the same thing, shift this to the origin, and then just divide it into triangles from there. They may not all be all identical, but all you need to use is then 2 vertices adjacent ones. So like you could use those 2 to find the area here. And then you could use those 2 to find the area here. And then you could use those 2 to find the area here. And just do 3, 1/2, this vertex and this vertex, this one and this one, this one and this one, add them together and get the pentagon or whatever it is. If you know that it's divided into equal ones, you don't really have to do a bunch of different. Do 1 and multiply by how many you need. But if you don't know if they're equal, this is a good way to find it as well. Versus if you think back to geometry, we would find the center and find a perpendicular line, the apothem down here, and we'd have an area formula that has to do with that. And usually we'd have to use right triangle trigonometry to figure out stuff to do with that. Again, you should get the same thing. We could technically do that. This is a nice way if you've got things graphed and you're using vertices and you don't need lengths really at all to do that. Okay, that's all that we have today. Again, problem sets due Friday with 2 lessons on it, this one and tomorrow's. So you could get started on that. Otherwise, you guys have a good rest of your day, and I'll see you guys tomorrow.
Mr. Smith?
Yeah.
Can you go up to the parallelogram problem? Can you explain where you're getting the numbers? Because I'm kind of confused.
Yeah, so I translated to put this vertex at the origin, which means everything moved 3 this way and 2 this way. So then I just moved 5, 3, left 3, down 2, and that's where I got 2, 1. And then I took 4, 7, left 3, down 2, and that's where I got 1, 5.
And then you only did that once because both the triangles are equal?
Yeah, and then, so basically if I had done 1/2, I'd have found this area. I could have done the other one using the vertices of the other triangle as well. What you'd find is that it's equal. So I just doubled that 1.
Oh, got it. Okay, that makes sense. Also, is there a way that I can see my test?